Okay, good. All right, so in this part of the lecture, I would like to now get a bit more concrete because the first part was a high-level introduction to the space. And now I would like to focus on Bitcoin, the protocol, not the currency, because I'm really focusing on the consensus protocol. And I will try to state and argue its security. Okay. All right. All right. So this is the abstract of Satoshi Nakamoto's white paper. By the way, if you have not read this white paper, I would strongly recommend it. It's only 9 pages long, but it's really beautifully written and contains many of the key ideas underlying the blockchain technology. It's amazing that one paper can invent so many different ideas. Okay, so let's take a look at this abstract. We can read a few lines here. A purely peer-to-peer version of electronic cash would allow online payment to be sent directly from one party to another without going through a financial institution. So without going through a financial institution is what we mean by decentralized. Okay. Now, it uses 2 technology. The first one is digital signature. The concept of digital signature was invented way earlier in the 70s, I believe. But the main benefit is lost if a trusted third party is still required to prevent double spending. So the double spending problem, as we'll explain later on, is really the consensus problem. So you can think of this Bitcoin uses 2 innovation. One is cryptography, which allows you to have digital signatures. And 2 is a new consensus protocol that solves the double spending problem. Okay, so I'll explain what that means. And the key technology used here is the notion of proof of work and the longest chain. So all the keywords I'm mentioning here. So all these words we'll explain in the next 45 minutes, 1 hour. Okay, all right. So back to this picture. Remember that these distributed nodes around the world is trying to come to an agreement on the ledger, on a ledger. Different nodes may have different views, but they will have to come to an agreement on what this ledger is. There are 2 problems being solved here in Bitcoin. One is data integrity. In other words, the data is legitimate and it's solved by digital signature. Okay, what does that mean? Alice is paying Bob 1 Bitcoin. But who is Alice? Alice, and what prevents someone else to pretend that he is Alice and pays that Bitcoin to Bob and pretend it's Alice and get a car, right? Get a Tesla or something, right? What prevents that? So the prevention of that is through this cryptography technology called digital signature. Only Alice, who has the private key behind the public key, can sign the message of paying Bob 1 Bitcoin. Another person who does not have Alice's private key cannot pretend to be Alice and sign that transaction, and therefore will not be considered a transaction from Alice's account. So this is what Nakamoto meant by using digital signature to make sure that the data integrity is maintained. However, there is a second problem that needs to be solved, is that now that the data has integrity, but now we have to have agreement across all nodes and across time. So different nodes should have an agreement on something at a particular time. And across time, if you have an agreement on something, you should not be able to revert that agreement and change to something else. And that's what data agreement means. And the focus of today's lecture is on the consensus problem, which is the data agreement problem. So this is the consensus problem. Okay. And this is what Nakamoto meant by the double spending problem. Okay, so I'll explain that. All right, so first, the protocol. The protocol works like this. It has two parts. One, it has a mining rule, which for a communication person, you can think of as the encoder. And two, it has a confirmation rule. As a communication person, you can think of this as a decoder. Of course, this is not a centralized encoder or a centralized decoder. This is run, this mining rule and confirmation rule is run at every node based on the data they received. So what you want is that the mining rule should be designed in such a way that when you decode, when you do confirmation, you have agreement across multiple nodes. Okay, so first, the mining rule. All right, so the blockchain, what is the blockchain? Blockchain is that you have a block. Each block contains some content, some information. In the Bitcoin case, transactions. The first block is the Genesis block. That's the beginning. Okay, so Nakamoto mined, or Nakamoto, when he came up with the protocol, it has the Genesis block. And different nodes now compete to try to generate a block to extend the Genesis. In this example, this one node generate a block, extend the Genesis, and etc. And keeps on going forward, okay? So as the blockchain extends, then it is coming up with a sequence of transactions, okay? The confirmation rule will tell me from this blockchain, how do I extract the ledger? Okay, so very importantly is that the blockchain so far does not mean that it is the ledger. The ledger is a function of this blockchain, but the rule is the confirmation rule, which we will discuss later on. Okay, all right, so it keeps on going. So here I'm just illustrating an example where there is only honest miners. Okay, I did not talk about attack yet. So here we have honest miners, and the protocol is so-called mining on the longest chain. What does that mean? Well, it's kind of strange here because there's only one chain. There's only one chain, and obviously the longest chain is this one chain. So you just mine basically means that you extend the tip of this chain. But when there's adversarial action, there may be adversary tries to put some blocks forking from the longest chain. So in other words, in general, you may see a tree. And what the protocol says is that everybody on this protocol should be always extending the longest path of this tree. Okay. All right, good. So that's the minus of the longest chain. Now, again, it turns out that the block arrival process is not deterministic. It is actually a random process. And if there's only honest people mining, then you can think of the arrival block as a Poisson process. And in Bitcoin, the average mining rate, lambda, is kept to be 1 block per 10 minutes. Okay, so 1 block per 10 minutes. Good. So that's what, so in other words, if there's no attack, then this chain will grow, like I showed earlier, without any forking. And it's growing at the rate of 1 block per 10 minutes, but following a Poisson process. So in other words, okay, so what's the Poisson process? What's the inter-arrival time of the blocks? What's the distribution of the inter-arrival time of consecutive blocks? All right, question for the audience. Extended chain equals copying the ledger. No, no, no. Extended chain means that you're adding more transactions to the ledger, potentially.
Exponential distribution?
Yes, exponential distribution. So the inter-arrival time of the blocks is exponential distribution. So this is rather mysterious. So we're still at a high level here. Mining, what does it mean? Why is it a Poisson distribution? Why is it the inter-arrival time exponential? That's a bit strange. Let's go to the 1 level lower. Okay, so to explain this mining process and why it's random, we have to explain the proof of work. Proof of work. Okay, so you have a blockchain here. So far, 4 blocks. You now have a new block that you're trying to mine. So imagine you are one of the many nodes. You're called a miner. Okay. So a miner, remember, takes input transactions. So it looks at the input and says, oh, okay, Alice wants to pay Bob 1 Bitcoin. Charlie wants to pay David half a Bitcoin. So he collects a bunch of transactions that he received. And now it wants to put these transactions onto the blockchain. Okay. And it puts it into this block. This is a new block. All right. So what does it do? It first looks at the hash of the previous block that it wants to mine on. So when I say mine on a chain, it means that it looks at the block at the tip of the longest chain. It takes the hash of the previous block. So a hash is typically 256 bits. In this example, only 0.0000749849888. This example. Prof. It then have a bunch of transactions. Alice pays Bob 1 Bitcoin, Charlie pays David half a Bitcoin, a bunch of transactions, which is just a bit string again. It puts it into the block and say, okay, I want to add these transactions onto the blockchain, okay? Now comes the proof of work. All right, so the proof of work, that's the following. It says that, okay, to put the block onto the blockchain, it will cost you some computation, okay? You have to solve a puzzle. Whoa, what's going on here? Okay, you have to solve a puzzle. So what is this puzzle? The puzzle is the following. First, it takes a hash function. So by the way, what is the hash function? Hash function takes an input, which is a bit string, and output a 256 bits number. Okay. And here the input bit string is the previous hash, the transaction bits, and a nonce, which is a variable, and it wants to make sure this hash value is less than a certain threshold. So this is the puzzle. You can think of this as a puzzle. Okay, that needs to be solved in order to generate, in order that the miner can generate a legitimate block. Okay, now, how do you solve this puzzle? So the cryptographer designed hash function to have the property that computationally, it is extremely difficult to invert this hash function to solve this inequality. So remember, the right-hand side is a 256-bit number. So this threshold basically means that it's a very small number. So the threshold basically means that you need, say, 80 zeros in the front, and then the rest can be non-zero. Okay? So that is what basically this threshold means, is that you need this hash value to be very small. If you can invert this hash function, then you can find an nonce which solve this puzzle. Cryptographer first says, no, we do not know of any efficient method of doing this. Okay, so what miners do is, well, we don't know how to invert this. So what they do is they would keep on trying different values of the nonce. Okay, so here we're rotating through multiple different values of the nonce until they solve the puzzle. If you want to get 80 zeros, you have to try many, many times before you can get 80 zeros, right? Many, many times. And that's the puzzle. And that's the proof of work puzzle. And that's why people have to have IEESc to do this computation very, very fast. Okay? Because once they solve this puzzle, then they can propose this block. Okay? And then what they can do is that they can, sorry about this error here. It should not be here, it should be here. What they can do now is that they can now propose this block to the rest of the network, to the rest of nodes. And the other nodes who receive this block will now check whether this puzzle is solved. Okay? And they will check. The good thing about this hash function is that computing it is very easy. Solving it is very hard. So these guys take extremely lot of computation to solve it. But to check whether the puzzle has been solved is actually very easy. And so everybody can check it and say, okay, good, this proof of work is done properly. I will now accept this block. That means that in my local memory, I will now extend this block on the longest chain, and now I have a longer blockchain in my local memory. Okay? Now, one can ask, so at the high level, what's the point? Why do you have to do this proof of work?
Sorry, David, just quickly to interrupt, there's 1 or 2 questions in the chat.
Oh, okay, there's some questions. How to detect the bad people in the blockchain? So most consensus protocol do not try to detect bad people in the blockchain. Okay, just think about it. It's a little bit like decoding. Most decoding algorithms do not try to figure out which bits has an error. You're just trying to decode the correct message. So this is similar here. Second, how big is the nonce? The nonce is also 256 bits. Also 256 bits. So all these are 256 bits number. And so you have many, many possibilities to try. Okay, good. All right. So let's think about it. First, why waste all this computation? What's the point here? Well, if you think about it, a basic property of Bitcoin is that you want to be permissionless, right? Permissionless. That means anybody can join. So to prevent the bad guys to completely overwhelm the system, you're basically saying that if you want to participate in this protocol, you need to spend some computation. You need to spend some energy. You need to have some hardware. That puts a barrier to entry in order to make people harder to join the system. Anybody can join, but if you want to participate, you need to spend some effort. It cannot be an effortless exercise. Otherwise, a bunch of people can easily attack you as well. Okay, so that's why you do this proof of work. So that whoever who can propose a block means that it has some computational power. And in fact, the probability that you get a block, the next block, is proportional to how much computational power you have relative to the computational power of the network. Okay, now let's think why. So now why is the block arrival process Poisson? Who chooses the puzzle? Nakamoto. Nakamoto chose the puzzle. It uses a particular hash function called SHA-256. So Nakamoto designed this puzzle. So I don't know who, because I don't know who's Nakamoto. Okay. All right, so question for you guys. Why is the block arrival process Poisson? Okay, so I should tell you that there's a property of the hash function, okay? A hash function has this property which basically says that if you give me the input, if you pick an input, then any computationally bounded algorithm cannot distinguish the output from a random number, random 256-bit number. So any input you pick, you can't really predict the output. So therefore, each time you try and announce, the output is like a totally random number. Okay? So now, exactly, because it's memoryless, then you're basically saying that each try has a very small probability of succeeding, and you try many, many, many times, then you succeed. That is basically an exponential distribution in the continuum where you assume that each computation is done very fast. All right, so let's see. Remember that when we saw this, let's go back to this thing here that we had earlier, this hash rate business, okay? All right, this hash rate business that we talked about. Let's see now what that means, okay? So before someone asks me what the heck is this hash rate, so hopefully my explanation is clear. So first of all right, what's terahash? How big is tera? How big is tera? People know? Sorry?
10 to the 12.
10 to the 12. All right, so 200 million tera. Let's calculate. It's 200 times 10 to the 6 times 10 to the 12. So how many zeros do we have here? 12. plus 6 plus 2, right? So we have 20 zeros. Okay? So what does 20 zeros means? It means that it's a lot. 10 to the power 20 is the number of hashes. It's the number of hashes that is being computed across the whole network of miners. That's what the total hash rate means. Every second, as we speak, there are of the order of 10 to the 20 computation of this hash function per second. Okay, it's pretty tremendous. It's pretty tremendous.
Sorry, does that include the verification?
The verification is not included, but it's trivial. The verification, as I mentioned, is a very, very easy compared to.
No, but that is a computation of the hash function still. So to verify. So I guess so that I was wondering whether that's also a part of the, that's
so this is 10 to the 20 computation of the hash function, right? So you're calculating this hash function 10 to the 20 times per second.
The verification also includes, but the verification also needs to compute the hash function, right?
Yes, yes. The verification also needs to compute the hash function, but you only need to compute it once when you receive the block. And this block only arrives one every 10 minutes. So it's a very small amount of computation. Okay.
David, another question. I posted it on the chat that I'll ask orally.
Okay.
At this large level of hashing, one would expect a sort of fluid limit to kick in and somewhat a straight line, but I still see jaggedness, randomness. So is there some explanation?
So the randomness, the inter-arrival time is exponential. Is that the question, or what? Sorry, what is the concern here? I didn't quite understand the question.
The concern is there is randomness, that I agree, but at this large level of hashing, when you scale it in this particular way, I would have assumed that there would have been a straight line, that you would see the number of hashes to grow almost linearly. You would not see this jaggedness. Looks like there is quite a bit of randomness.
Okay, okay. Maybe I should clarify what. Oh, so you're talking about the plot right now. So I should clarify. This plot is not the total number of hashes. It is the total hash rate. So the hash rate is being changed here, actually. So in the simple model that we're thinking about, the hash rate is constant. Okay, so if you look at a particular point in time, there's a fixed hash rate. And given a fixed hash rate, you have an inter-arrival time, which is exponentially distributed, because although there are many, many tries, each try has only a very, very small probability of succeeding. So this is like the Poisson approximation, right? Very small chance of success. And so the time is exponential. Now I should explain why this hash rate is changing over time. Because actually, I just mentioned that the inter-arrival time is fixed at an average rate of 1 block every 10 minutes. So why is the hash rate actually changing over time? I think that's maybe a better way of thinking about this question. So why is it changing over time? Well, it has to change over time because people can join and leave, right? But the magic is, why is the block time still kept at 1 block every 10 minutes? So, all right, so a question for the audience. Is there any way to keep the block mining rate at 1 block every 10 minutes? So in other words, a fixed Poisson rate, while although the amount of hash rate could be different. Is there any parameter we can adjust here to match that, just to make sure that we understand this puzzle?
Yeah, the difficulty of the problem could be adapted to keep the success.
So what is the parameter here in this slide, which determine the difficulty?
The threshold?
The threshold. Yes, so the threshold can be adjusted. So this amazing thing about this protocol is that the threshold could be adjusted, and we'll explain later on why it's important to keep it the block time to be a constant. Although the hash power, starting from Nakamoto time to now, has increased by 10 or 12 orders of magnitude, the threshold keep on adjusting to make the puzzle more and more difficult in general. And when China banned Bitcoin, the hash rate dropped. The threshold is now easier. In other words, a bigger number. And then the block mining rate retained at 1 block every 10 minutes, okay? All right, so that we can explain a bit later. But
there's one more question in the chat. There's
What if someone just makes a single transaction? Can we form a block out of just one transaction? Sure you can. Sure you can. However, it turns out that there's a reason why the miner is generating a block in the first place. Number one, it is getting a block reward. And that reward is independent of the number of transactions. But two, it is also getting transaction fee. And that is proportional to how many transactions you put in. So there's no point in just putting one transaction. You should put as many transactions that you have received. So you keep on mining, and as you mine for a long time, you may receive more transactions, and you should keep on putting in, unless you saw that transactions already in the ledger. You should try to keep on fresh transaction in, because you just get more transaction fee. Is that okay? All right. Okay. All right, so that's the mining process. And because of this sort of sequence of hashes, it is impossible for an attacker to go and replace one block in the middle of this blockchain. Because if you have to replace it, a block, you need to change, you want to change the content, right? For example, you may not like a particular transaction, you want to remove that transaction, or you want to replace that transaction by another transaction. That is no good. That's a safety attack, right? Because you've already agreed on something and then you change it. But this proof of work makes it extremely difficult for you to do that, because the proof of work puzzle already has the transaction in there. And if you try to change the transaction, you cannot satisfy the same hash puzzle anymore. And so changing just one block in the middle doesn't work. But now we're going to talk about more interesting attacks that actually works and we have to worry about. Okay, so now I'm going to talk a bit about the confirmation rule. So we talked about the mining process, the encoding rule. And now we're going to talk about the confirmation rule. In other words, in the blockchain, what part of the blockchain I should consider the ledger, right? The confirmation rule is the generation of the ledger. So let's start with a simple one. A simple one is the following. It's called instant confirmation, okay? So the blockchain grows, and then you receive a block. That block have a transaction, many transactions, in fact. Typically, a block in Bitcoin has about 1,000 or 2,000 transactions. But now I see a transaction. I say, Alice pays about $1, 1 Bitcoin. Instant confirmation means, yes, this block, once I receive it, once I check the proof of work, it enters into my local view of the ledger. That's what instant confirmation means. In practice, that means that, hey, the transaction is considered confirmed, and therefore I will have to pay the goods. So Alice pays Bob 1 Bitcoin. That means Bob will give the card to Alice upon confirming. Okay, is it a good idea? So this is a confirmation rule. This gives a rule of general ledger, which means that the entire blockchain of the longest chain, in my view, is now the whole ledger, okay? Every time I receive a new block, the ledger grows by 1 block. Is this a good confirmation rule? Okay, it turns out that Nakamoto understood that this is actually not a good confirmation rule. Okay, not a good confirmation rule. Now, why is that? Why is that not a confirmation rule? Okay, so here's a potential attack. All right. So an attacker, remember, is someone who does not follow the protocol. Okay. Now, what does the attacker wants to do here? The attacker says, okay. The attacker's actually is Alice. Okay. So Alice, what was Alice trying to do? Alice, on this rule, under immediate confirmation, pays Bob 1 Bitcoin. Bob confirmed immediately and gave the card to Alice. Alice now wants to use the same Bitcoin that it pays Bob to pay Charlie to buy, I don't know, a house. Probably can't buy a house using 1 Bitcoin, but to rent a house, I don't know, for a year, for a few years. Okay, whatever. All right. So what it does is that Alice will now mine, say, 2 blocks in private. It tries to mine 2 blocks in private. And it would not release these 2 blocks until the block here is received at node so that they have a confirmation. And then once this confirmation happens, Alice will now release these 2 blocks to the rest of the network. Okay? And then what will happen? Let's see. Now, this will become the longest chain. Yes, that's the longest chain rule. Where will the other miners continue mining on? The longest chain. So what happens to this transaction? Alice pays Bob 1 BTC. What happens to this transaction that is in this confirmed block? It's gone. It's no longer in the ledger. Instead, what is in the ledger could be Alice pays Charlie the same Bitcoin. Okay, each Bitcoin is basically defined by a private public signature pair. Okay, so now the new ledger is Alice pays Charlie 1 Bitcoin. So Alice now got the car from Bob, but at the same time could buy something else from Charlie using the same Bitcoin. This is a horrible situation here, right? Because this attacker is now double spending the Bitcoin. So this is exactly what Nakamoto meant by the double spend problem. You are using the same Bitcoin to pay twice, and that is because your ledger that was agreed upon earlier is now no longer consistent with the new ledger. In other words, this old ledger is not a prefix of the new ledger. And so transactions disappeared. Okay, so this is exactly an example of a safety attack. Okay, now let's look at the situation here. Does this event happen with what kind of probability are we talking about? Is this possible actually? Is this attack actually possible? Can Alice get 2 blocks while everybody get 1 block? Well, it depends on how much hash power Alice has. Okay? If Alice has 90% of the total network hash power, then obviously it's very easy for it to generate 2 blocks, because the rate at which it generates block is proportional to its hash power. Yeah? The more hash power you have, the faster you can solve the puzzle, and the faster you can generate the block. So you got 2 blocks, whereas 10% of the hash power, the honest guys, get 1 block very easy. Okay? However, the problem of this confirmation rule is that even if Alice has, say, 5% of the hash power, not 90%, but 5% of the hash power, the probability it gets 2 blocks is still not negligibly small. Because, you know, this is a exponential, a Poisson, a random event, right? So the probability you get 2 blocks before the 95% of the miners get 1 block is not a negligibly small probability, maybe 1%, maybe 2%. It's not a very small probability. If you want a robust network, you want this probability to be 10 to the minus 6 or something, you know, minus 5, not too small. So that means that this instant confirmation rule is actually not very robust, even with a small amount of hash power of the attacker. So Nakamoto was not very happy with that. And so the question is, how do you change the confirmation rule to make it more robust to such attacks? Okay, any thoughts how we can make it more robust? So we're following Nakamoto's thought process. So instant confirmation means you receive a block. Confirm after a few blocks, maybe, right? Actually, it's very intuitive sense, right? You don't confirm immediately. Let's see if there are a few more blocks after this block first, and then confirm. Let's see if it works. And this is the K-deep confirmation rule of Nakamoto. So Nakamoto says, don't confirm immediately, but confirm only when the block is K-deep. So what does that mean? Let's think. So it waits until K blocks is in the blockchain, in the view of the node. Then you confirm the ledger up to this point. Okay, so therefore what the ledger is a prefix of the entire blockchain, the longest chain, chop off the last K blocks. So that's the ledger, and that's the confirmation rule, K deep. And K is a parameter that can be chosen by the protocol. Okay. All right, so why is this a better protocol, a better confirmation rule? All right, think about it. How would Alice attack the system with this new confirmation rule? Well, if Alice, while Bob received this K, so first of all, there's no point in Alice attacking the system immediately by showing a 3 blocks when you have you don't have K block deep, right? Because at that point you have not even confirmed yet. So there's no point in him showing a longer chain. So Alice can only kick out this block from the ledger if it can in private grow more than K blocks. while the honest miners are getting K blocks. Yes? Okay. All right. So Nakamoto calculate what is this probability. So Nakamoto paper actually has a section we've done a probability calculation. Okay. And so he did the calculation and he said, let's assume the adversary has 30% adversary power. So you can do this calculation for any percentage, but Nakamoto just example calculated for 30%. What does that mean? That means the attacker has 30% of the hash power. The honest nodes have 70% of the hash power. That means on the average, the attacker will generate a block about 30. So let's say the honest guys are generating one block every 10 minutes. Then the attacker will generate the block at a ratio of 3 to 7 times 10. So maybe around, I don't know, 3 to 7 times 10. So maybe around 21 minutes. Okay, 21, 22 minutes on the average. But the attacker can get lucky and get a block shorter time than 22 minutes. Maybe 15 minutes can get a block, 8 minutes can get a block. But Nakamoto did the calculation. As K increases from 0 to 5 to 10 to 15, epsilon, which is the probability that the attacker succeed in this attack, okay, becomes smaller and smaller. And when K equals 50, the probability is 10 to the minus 6. 6 times 10 to the minus 6. Okay? So that's the calculation Nakamoto did. Now, we are information theorists, and we look at this calculation. This is a phenomenon that should be somewhat familiar to people who do information theory. So what is the phenomenon that is described? What's the qualitative phenomenon that's described by this table? People know? There's a law, there's a probability law that governs sort of the qualitative nature of this table, which is this probability gets smaller and smaller as K becomes larger and larger. People know? What's the law? What's the most important law in probability? Let me answer this question. Let me discuss this question first before we answer. Law of large numbers. Thank you. Right? There's a law of large numbers. Because the attacker has only 30% adversary power, right? If you confirm immediately, then it may get lucky and generate 2 blocks while you get 1 block. That's not a 0 probability event. Okay, maybe 5% probability. But if you now ask him to generate, while you generate 50 blocks, you ask him to generate more than 50 blocks, wow. And it only has 30% adversary power. That's really difficult because of law of large number. Because when you get 50 blocks, he will probably get only 3/7 times 50, which is around 20 blocks on the average. But now you're averaging over so many blocks, that's also highly likely that that event will happen. Okay, so this is a law of large number. All right, so there's a question here by Lalita. Does that mean that Alice cannot do another transaction till its previous transaction is confirmed? No, no. Alice can do any transaction it wants. The thing is that if the transaction that Alice does, it is after, right? So suppose Alice puts a transaction in, like Alice pays Charlie 1 Bitcoin. Okay. Suppose on the ledger, we have Alice pays Bob 1 Bitcoin. And now Alice tries to put in the ledger okay, 1 Bitcoin. So double spend. If the double spend is along the same ordering, same ledger, then the second transaction is considered invalid because Alice already paid Bob 1 Bitcoin. There's no more Bitcoin anymore. The Bitcoin is spent. The double spend is automatically rejected by everybody. The double spend problem only occurs when it occurs on a different fork. Because on this different fork, Alice pays Bob is no longer there in the previous history. You see the difference here? So Alice can make transaction, but it will have to pay another Bitcoin. So Alice has maybe many Bitcoins, but each Bitcoin has a different signature associated with it. So Alice can certainly spend another of his Bitcoin, but it cannot spend the same Bitcoin twice. Okay? Ladita, is that clear? All right, good. Okay.
Sorry, David. Okay, so we're at 11:07 here.
Oh, 11:07 already. Yeah, okay, sorry.
So what shall we do? Because I think we're supposed to have a question answer session, but we can continue if you think you want to reach a point and we, which would be a natural break point.
Yeah, there is a bit of a, if you can give me 10 more minutes, there's a natural break point actually. And maybe I can take some more questions after that. I can stay a little bit longer. I don't know. Does the meeting, is there a next talk after 10:30 or sorry?
Yeah, I think 11:30 there is a talk, but we may have to.
So let me do a few more minutes and then maybe I can open up the floor for 10 minutes of questions. I think there were already quite a few questions in the middle, so I think I may have consumed some of my Q&A time already.
Sure.
But I think it's good to have questions in the middle also, because otherwise it just got very boring without any questions. Okay, all right. So basically Nakamoto showed, so I'm going to do the calculation right now, how this calculation will be done. So I want to introduce some notation here, so which we will use later on. So total mining rate is, the notation is lambda. The honest mining rate is lambda H. The adversarial mining rate is lambda A, and the adversarial fraction beta is equal to lambda A over lambda, which is equal to lambda A over lambda A plus lambda H, okay? All right, so lambda equals lambda A plus lambda H, and that's the relationship, and those are the key numbers here, okay? So 3070 means that beta, okay, beta is 0.3, okay? Okay, all right, so how does Nakamoto do this analysis? Basically, this is the calculation he does. He said, okay, suppose the adversary is able to generate K blocks, okay? K blocks, and it looks at the inter-arrival time T1A, T2A, up to TKA for the inter-arrival time to generate these blocks. And now it looks at the inter-arrival time for the honest node to generate N blocks. And he said that attack success, the attacker succeeded if it can generate K blocks before the honest node can generate K blocks. So in other words, it can generate N less than or equal to K blocks. So that's the calculation it does. It's a pretty straightforward calculation. Nothing very difficult, kind of elementary calculation, but that's what he did, okay? All right, so what does safety means? So now we can define a notion of safety. So a block B is said to be safe if once it enters a ledger, then it remains on the same position in the ledger in the view of any node at any future time, regardless of the adversary's attack. Okay, so what we showed, and actually what Nakamoto showed, is that by choosing K, the confirmation depth K, large enough, then with high probability, the protocol is safe. However, the tricky thing is that he only analyzed this under a specific attack, which is the so-called private attack. Okay, what is this private attack? The private attack is basically that the public chain continues to grow here, public. The adversary mines these blocks in private and then release it later. Okay? So that's the attack that Nakamoto showed. So here, I would like to emphasize a very important point here, is that you cannot prove the safety of a protocol by just looking at one or a few specific attacks. You have to prove that your protocol is secure under all possible attacks. And that's what a security theorem is. And that's why proving a protocol is secure is rather difficult. Because first you have to set up a model that allows you to describe what all possible attack means. And then you have to prove that within your model, and that model should be acceptable. It's not like your own model. Everyone should agree on that model, that you can prove the security under all attacks in that model. So that's why if you go and read security of these protocols, they are very long and complicated because it's not so easy to set up a model, and it's not so easy to write down this class of all possible attack. Okay, so what happened was that Nakamoto basically is not a consensus expert, but this is the attack that he thought is probably going to be quite bad. He analyzed it and said, okay, if I use K large enough, then this attack is okay. In other words, the probability can be made arbitrarily small, okay? People came afterwards, though, who are consensus expert and look at this protocol and say, wait a minute, Nakamoto did not do a proper security analysis. He only looked at one particular attack. What about other attacks? For example, this is another type of attack, okay? So in this attack, the honest and the adversary blocks are kind of mined in an interleaving manner. Okay, so maybe the attacker is trying to sort of build two chains in parallel and keep it balanced. So it's no longer keep a bunch of blocks in private and then release all of them later, but maybe it interacts with the honest node in a very complicated fashion and start building these two forks and forces the blockchain to go back and forth between these two forks. Maybe that's a worse attack than the private attack. Nakamoto did not analyze this one, okay? And so in 2015, about 6 years later after Nakamoto, a 50, 60-page paper appeared, okay? Which basically showed that Nakamoto analysis is correct, okay? So actually what does Nakamoto showed? So Nakamoto showed that if the adversary, so what, okay, so let's think about Nakamoto's analysis, okay? It showed that under some condition, the probability of a block being confirmed and then deconfirmed later by the private attack is very small by choosing K large. What is the condition on beta? So let's ask the question. Under what condition on beta does the probability epsilon goes to 0 as K goes to infinity? Okay, let's try to answer this question, and then we'll continue tomorrow. Okay, so let's answer this question. Under what condition beta? So reminder, what is beta? Beta is the adversarial fraction. Okay, so what do you think? What's the condition? Suppose the adversary has 90% power, beta is 0.9. Okay? Do you think that the probability will go to 0 as K goes to infinity? No, right? Because the adversary has more power. No matter how long you wait, the adversary will, in fact, the longer you wait, there's more certainty that the adversary will get more blocks than you, right? So it doesn't matter. Your probability will not go to 0 as K goes to infinity. In fact, your probability goes to 1 as K goes to infinity. Epsilon will go to 1. For sure, the attacker will be able to revert you. Yeah? So information theory asks the question of capacity, right? What is the maximum performance you can achieve to drive the probability of error 0, maximum communication rate? So here, there's a notion of capacity, which is what's the largest beta that the attacker can have such that K will drive the error probability, the confirmation probability 0. Okay, so what is that threshold? Not 90%. Any suggestion? %50%, right? Yes, because at the 50% threshold, the adversary and the honest is equal. As long as the adversary has slightly less than 50%, then as K goes to infinity, eventually the adversary will lose out. So 50% is exactly the analogous of capacity of the system, but under this private attack. Okay, so under the private attack, the condition for success is beta less than 0.5 or equivalently lambda A less than lambda H. Okay? Now, the question that people had later is, this is under a particular attack, but maybe there are even worse attacks which make this threshold even smaller than 50%. Maybe 30% is a threshold. Maybe 33.3% is a threshold under some even more severe attack. Okay? So tomorrow, I will continue by answering this question. Is there worse attack? Or was Nakamoto smart enough to already figure out kind of the worst attack? Okay, so let's end it at this point, and we'll come back to this question tomorrow. Good?
Yeah, perfect. Yeah, great, David. I think that's a very nice place to stop. Are there any questions? So maybe, Satyajit, how do you want to handle this? Shall we just take whatever 10 minutes of questions there are now, and then 11:30 we have the talk?
Yeah, sure. We will start at 11:40, that poster session. So we have time.
Okay, fine. So we can have a few, maybe 10, 15 minutes of questions. Is that fine, David?
Yeah, great. If there's any question, please ask so that we can clarify all potential points of confusion. Please.
Yeah, students are particularly encouraged to ask questions. This is a summer school. Being a school, it's good to have students ask questions. So there is a question in the chat now.
Yeah, that's a really great question by Lolita. The question is it possible to design a protocol with different level of trust for different transactions? Okay, so let's think about this in the context of Bitcoin. So you can think of the level of trust can be dictated by the parameter epsilon, right? Epsilon is like your level of reliability. If epsilon is 10 to the minus 1, that means with probability 10%, your transaction will be deconfirmed, right? If epsilon is 10 to the minus 6, that means with probability 10 to the minus 6, your transaction will be deconfirmed, right? So epsilon is like your level of trust. So the question is it possible to design a protocol with different level of trust? And the answer is yes. In fact, Bitcoin itself is this protocol. Why? Because, you know, the K, who chooses the K? Let's think about it. It is Bob who chooses the K. Who is Bob? Well, Alice pays Bob 1 Bitcoin, right? Bob has to make a decision. When does it consider that Bitcoin has entered its account and therefore it can pay the car? It can give the car to Alice, right? So therefore, it is Bob, the client, who actually picks K. So therefore, different clients can pick different K depending on the importance of the transaction. If the transaction is coffee, then it should not have to wait so long. You see, K is a price to pay because you have to wait longer, right? If you want the thing to be 5 blocks deep, you have to wait on average 15 minutes. If you have to wait until 50 deep, then you have to wait 500 minutes. So different clients or different nodes can choose different K, no problem. So Bitcoin already has this property. Is the attacker someone who is in the blockchain? Now, now I have to clarify what this question is. There's no one in the blockchain, right? Miners, they mine blocks. They propagate these blocks to other miners. Other miners receive these blocks and add the blocks onto the blockchain. So every node keep in his local memory the sequence of blocks that is received so far. That's the blockchain. And attacker is one of these miners or several of these miners. And they decide to, as a group perhaps, decide to, instead of going on the honest chain, went on a fork to try to fork off the system to change history. That's the attack that we described earlier. Okay. Can there be 2 or more numbers generate same hash? Yes, there can be. There can be, but I don't know what the implication of this is in the. What if attackers and block with difficult threshold? Now, what does that mean? You mean they use their own threshold? Okay. All right, so that's a good question. So remember we said that the threshold is actually adjustable in Bitcoin, right? But how is this adjustment going to be made? It turns out that this adjustment is itself a function of the blockchain that you've agreed on, the ledger you've agreed on, the blockchain you've agreed on so far. So therefore, first you have an agreement, and then everyone will agree on how the difficulty threshold should be adjusted based on some data on the previous block. So you can't just go and set your own difficulty and make your block very easy, right? No one will accept it. Because everyone will be looking at the blockchain and then use that to calculate what is the current difficulty level. So basically, there's a sort of an adaptation here, is that if people find that the blocks are generated very frequently, then the difficulty will be gradually adjusted to make the puzzle harder so that the block generation rate will be slowed down. But everyone will look at the blocks to figure out how this frequency is. Okay.
Sorry, David, before you ask, sorry, before that question, I think there is a question that should be probably addressed before this one. There was one slightly up. If you just scroll up slightly, you'll see there is a basic question that should be addressed, I think, before you go on to anything more.
Oh, okay, there it is. I missed it. Sorry about that. Could you please explain the mining rule and confirmation rule briefly? Okay. The mining rule is the state of the system is everyone keeps track of a tree of blocks. Each edge of this tree is defined by a proof of work puzzle solution. Okay, so everybody has a tree. And the mining rule is that the honest miner should always mine on the tip of the longest branch of this tree. They should not go and mine on the shorter branch, okay? In other words, they should always keep on extending the branch. The point is that everyone tries to make this tree as little branch as possible to focus all the mining power on sort of one line. Ideally, everyone should have one line, but you know, there may be attackers that's trying to confuse you. Okay, that's the mining rule. Confirmation rule is that everyone looks at the longest chain, the longest branch in the local tree, okay, and chop off K blocks from the tip and confirm the ledger to be the prefix of the remaining of the longest chain. Okay, is that, Navin, do you think I have answered that question? It is important, but it is a,
yeah, I mean, I guess like if you don't understand that, it is difficult to understand anything further that goes on. I think
yes, it is a very simple protocol, but that should be understood. Yes, it's a very simple. I should say that it's quite simple, right? Because I've already explained the whole protocol in 1 minute.
Sorry, so confirmation happens like again at like you know, in a decentralized manner.
Yeah. So the confirmation is actually something that is run. So you can think of the blockchain is maintained by a bunch of miners, okay? But everybody who has transactions in the blockchain can go and query and figure out, okay, what is the blockchain right now? And then they can apply their own K-deep confirmation rule that they like on the blockchain that they received, and then confirm up to K, and then, right? So they would say, okay, hey, I'm Bob, right? So I'm Bob. I go and query around the blockchain network and figure out, okay, so this is the current blockchain, this is the longest chain. And then I check, hey, where is the transaction that Alice pays me 1 Bitcoin? So I search on this chain, and I find that this thing is 10 block deep in the longest chain, okay, this transaction. Then I say, okay, 10 block deep, I'm happy. Then I consider the transaction to be confirmed, and then I go and give the call to Alice. But if I'm a more cautious guy, maybe I should wait for 20 block deep. Okay, In practice, if it were an exchange, they would go for more block deep, because exchange would take all these transactions more seriously. So yes, so in that sense, is everyone implements the local confirmation rule. To simplify the discussion, I just assume a same K for everybody, just to simplify the notation a little bit. But this K is actually can be locally adjusted. Okay. Computational power is enough. Miners, I don't know whether they have any brain power, because miners are just ASICs, you know, they're not, yes. Is there a maximum value for the number of transactions? So there's a maximum block size that is around 1 megabyte, okay? So that puts a limit on how many transactions you can put in. The transactions are somewhat variable in size, but there's a minimum and maximum. So the range of transactions, I believe, is of the order of 1 to 4,000, if I remember correctly, a few thousand. If a hash can be generated by 2 different numbers, then the number is not uniquely recoverable but from looking at hash. I still don't understand that question, actually. We never, so let's see here. Yeah, I don't understand the question.
So, sir, is it a requirement to recover this number by looking at a hash? Is it required?
No. It's never. All the computation is forward computation, right? Think about there are two different types of people computing this hash function. One is the miner, okay? One is the miner who is trying different value of the nonce and compute hash value many times. So each time is a forward computation, never backwards. The second type of people who are interested in hash function is the verifier. It's someone who wants to verify whether the blockchain they receive is valid. To do that, they have to prove that, they have to check whether every proof of work connecting adjacent blocks is valid. So to do that, they will compute the hash function based on the nonce that you put into the block and check whether it is indeed less than the threshold. Okay? Okay, that's a good question from Jerry. What if the chain forks? In this case, the honest mining power may naturally split. Do 80% honest miners still suffice? Okay, so there's an implicit assumption that I've made in this analysis, which is that honest power never split. Okay, which means that all the honest power is mining on the tip of the longest chain, which basically assumes that every miner, honest miner, have exactly the same view as where this tip is. Okay, so implicitly, I'm assuming that the delay in the network is very small. Okay, very small compared to what? Very small compared to the rate at which the blocks are generated across the whole network. In other words, very small compared to 10 minutes. Okay, because if you think about it, if the delay is very long compared to 10 minutes, then it could be that someone has already generated a block and I haven't seen it. I'm still mining on the previous block. And so now the honest power may split. So implicitly, I'm making the assumption that the mining rate is much slower than the delay of the network. Tomorrow, when we talk about latency, we'll go deeper into this issue. But assuming that you can, at this point, assume basic delay is 0, then there's no split of the honest power. So everybody, honest people, would mine, focus the power 80% on the tip. Yeah, so the Vinay question is similar. What is the block time 10 minutes? It is 10 minutes in order to make this block time much slower than the delay. So Nakamoto basically assumes that, hey, maybe the delay is no more than 1 minute. So we set the mining rate to be 10 minutes to make sure that the honest power do not split. And in fact, this is a very important point tomorrow because that is exactly why Bitcoin is so slow. And our effort of speeding up Bitcoin is essentially trying to overcome this issue.
Okay, thanks a lot, David. I think it's a good point to stop here, and we can pick this thread up again tomorrow. Because I think the next talk, we're running up against the next talk in another few minutes. So thank you for your time. And like, I guess it's sort of dinner time, probably a little late for you, I guess. Huh? What is it like?
It's 11 o'clock.
11 o'clock, okay.
At night.
Yeah. All right. Well, thanks for keeping up to this point. Staying up and hopefully we will not keep you up so late tomorrow. I think you only have one lecture in the morning, so it'll be short, like you'll have early, you can get to bed earlier. So with that, let me thank David for his lectures for today, and we will reconvene for his lecture again at the same time tomorrow morning.
Cool. All right.
But we will now move, so Zoom will close, and I guess we'll have to go back to the AirMeet platform for the next talk.
So yes, we'll use the same Zoom. We'll use the same Zoom for tomorrow.
Yeah, we will use the same Zoom link for tomorrow.
For my lecture. Thank you.
Thanks a lot, David.
Bye-bye, everybody.
So we have poster sessions now. So we'll meet at AirMeet. Please log in there, and we'll start that session. Thank you.